Thank you so much for watching this online video tutorial. Like, comment, and share, as well as subscribe to our channel at Good Better Best Online Videos for more video content. Alright, hello grade 9. So we're just going to have a look at the physics paper of South Peninisula. Thank you to them for allowing us to use their papers in our videos. They're so kind. And what we're going to do is a 2018 paper, and we're just going to go through some of the MCQs just to get us warmed up and ready for the paper. Okay, so here it is. Hope we can all see. Let me zoom in slightly. 1.1.1, which two factors affect gravitational force? Okay, well, in our study, when we did forces of gravity, okay, there's gravitational force, magnetic force, and all those different types of forces. Under that section, we can definitely see that option C and option D do not apply. Because in grade 9, we haven't done anything with regards to velocity. We haven't chatted about momentum, which is only introduced in grade 12. So it cannot be C or D. We know the formula for calculating a person's weight is, I'll write it on the side here in a different color, is W is equal to mass times gravity, okay, which is the weight in newtons, mass, which is in kilograms, and gravity, which is in meters per second squared. Okay, so we need to find out which factors affect the gravitational force, which is obviously weight. Okay, now it cannot be mass and velocity, because we haven't done anything with velocity. There's no velocity in our formula. Therefore, by process of elimination, it is option B, which is, okay, let's just keep it yellow, mass and distance. The reason being is that the closer the objects are together, the stronger the gravitational pull, which means the stronger the gravitational force will therefore be. Alright, so it is mass and distance, which is option B. Next question. In case of filament lamp at higher voltages, resistance of lamp either decreases, increases, remains the same, varies depending on the filament. This question is a poorly asked question that if I get this question wrong, it's also because I did not understand the question. I think some part of the question must be missing when they scanned this paper in, because 1.4, the question is also missing somewhere, so don't know where to find that either. So it's probably should have appeared here, but it didn't appear. So what I understand about a filament is that if you increase the voltage, usually the filament is only designed to handle a certain amount of voltage. The light bulbs will tell you how much voltage it can go through. If the voltage is obviously too high, the resistance will not be able to compete. Alright? Will not be able to compete with the voltage, and the bulb will either blow, the filament will either blow, or it will stop working, go out. So one of the options that I think the resistance of the lamp at higher voltage, depending on the filament, okay, should not change if the voltage is increased. So I'm going to say option C, because the filament comes out only ready to handle a certain amount of voltage. But something's pressing me in my brain to maybe check this question again. Okay, in case of filament lamp at higher voltages, resistance of the lamp. Okay, well now I'm looking at this question in a different light. So what some lamps obviously have different voltages. I have a lamp that has a 240 volt lamp, but some lamps may have a a smaller amount. Some lamps may have a bigger amount, or a more than or greater than. So actually I'm going to change my answer from option C. I'm going to rather use option D. Oh, right, let me make this bigger. I'm rather going to use option D to say that surely the filament should vary depending on the varies depending on the filament. Surely. I'd rather say that, that answer. Okay. 1.1.3, in a series circuit, which of the following quantities remain the same throughout the circuit? Current and voltage, current, or none? For 1.1.3, it is option A, which is current. Current always remains the same in the circuit. In other words, the current that's applied in the circuit will not change. Okay, unless you change the battery or you change the voltage. Voltage of the circuit is usually supplied from the battery. Okay, but current stays the same no matter what or no matter where in the circuit. And if you go to 1.1.5, 1.1.5, when you are at home, because we don't have 1.1.4's question, when you are at home, turning off a light usually does not turn off your TV. This is because, and someone said it off air, option A, most electrical devices in a house are on parallel circuits. Okay, so that means that if I switch off something in one room, the whole house will not go off. If it were all in series, one component that's out would shut down everything. So 1.1.5 is also option A. Okay, right, so now that we're all warmed up, we're going to skip the 1.2 and 1.3 because that's just basically simple one-word answers. Question 2, this is actually more chemistry. Okay, this is taught in grade 12, so grade 12 chemistry. Obviously the questions that they're asking is more on a grade 9 level. Okay, but I've not formally taught this and have not seen this in the syllabus for this here. So we're going to ignore question 2 and we're going to go straight to question 3. Okay, so question 3 asks for a definition. It asks us to please go ahead and define what resistance is. Okay, so how would we go ahead and how would we define this? Let's just go and pop it in our answer here for question 3. I'll start the definition off. We get the white color back. Question 3. Let's just think it's 3.1. And let's keep the yellow color, or let's maybe move to orange. Okay, well, definition of resistance. Okay, we know what a resistor is. A resistor, of course, is a component of electric circuits. But resistance, okay, or electrical resistance, okay, this is how we would start by answering this question in an exam setting. Electrical resistance describes, okay, how an electrical conductor how an electrical conductor, for example a wire or whatever, tries to stop the flow of current. Okay, how it tries to stop the flow of current. Okay, and another one that we can add on to that, sorry, I'm not sure how to get rid of this. There we go, it keeps popping up when I hover over that thing. Stop the flow of current in a conductor. Okay, so that obviously current can't flow so easily. Okay, but that part should be fine or acceptable for describing resistance. Question 3.2 says write down the symbol of the unit, okay, in which resistance is measured. Now we know resistance is measured in what? Can someone just shout it out to me? Ohms, yes, measured in ohms. Fantastic. So 1 ohm, okay, is for example is a resistor value or quantity. So they ask you to draw the symbol, all right, or write down the symbol of the unit in which it's measured. For 3.2, that's easy, right? 1 ohm is the name. Sorry, right, ohm is the name. Okay, but what they actually want is that if you get a value, you need to write the symbol. Okay, it's that. Okay, obviously it's much easier to write it. There we go. That's much better. Just fix that last part there. There we go. Okay, looks something like that, and that is actually what they're looking for. So this is what they're looking for, and that will get you a mark. Okay. can write it like that as well to say, okay, 1 ohm, this is the symbol for how it's written, and they should still give you the mark as well. Okay, let's move on to 3.3. Okay, 3.3, the question is over here on this side. Okay, but that's how the circuit looks with the ammeter, voltmeter across a resistor. An investigation was conducted to determine the relationship between the current going through a resistor and the potential difference, which is voltage, across the same resistor, when the temperature was kept constant. Okay, so we've got our battery there, ammeter in the circuit, resistor, voltmeter across. The following results were obtained. Okay, voltage changed here, 3, current. Used all the information to answer the following questions. Okay. So you got to plot a graph of voltage on the x-axis and current on the y-axis. And then you need to give a research question for the investigation. This will be a great question. What's a research question for it? And identify the controlled variable. And then let's also explain how the following factors obviously affect the resistance of a wire. So that's basically remembering the factors of resistance. Okay, and I think we answered a question like this somewhere last week, I think, as well. Okay, so maybe you don't have to do that question formally, but plotting the graph, maybe we won't even need to do this question, because I'll tell you why. We all know how to plot a graph, but formulating a research question is that, okay, we've got these results, so almost like what's our question that we're trying to obtain here. Okay, so give a research question, and then the variable that's in the experiment that can be or should be controlled. Okay, so that's just a question to think about. We won't necessarily do it now. Actually, I've decided I'm not going to do the rest of 3.3 because this is very easy. But question 4, let's have a look at it. So we could just get used to the type of questions that's been asked here. Okay, study the following circuit below and follow the question. So we got resistors that are identical. Each cell has a voltage of 6 volts, so that's 12 altogether, 2 amps, and there we go. Okay, well, that was easy. 4.1, determine the total voltage of the circuit. They've told you here that each cell has a voltage of 6 volts. So what's the total voltage of the circuit? If there's 2 cells and one of them are 6 volts and they're identical, so total voltage is
12.
Well done, 12 volts. Okay, if you wrote 12 without the V next to it, you would have gotten the question wrong. Don't forget your units, please. Okay, they're asked to give the readings on ammeter 2 and on the voltmeter. Well, the reading on ammeter 2 should be the same as ammeter 1 because current is the same no matter where they are in the circuit, and it's a series circuit as well. The voltmeter, though, if each of the cells has a voltmeter of a voltage of 6 volts and all the resistors are identical, then the voltmeter should equal to the total voltage in the circuit. So if I make the assumption that all resistors are identical, I'm not told the value of each of the resistors. Okay, I'm not told that. Okay, all I'm told is that they are identical. So what I can assume is that if they are 1 volt or 1 ohm each, then I should be getting a reading of 12 volts because that's the total volt that displays in the circuit. Okay. What will the total voltage of the circuit be if the cells are connected in parallel? Well, the cells are never connected in parallel. Okay, cells are always connected in series in any case. So that's your reason. Cells are never connected in parallel. Okay, they're always connected in series. Compare the ammeter of the voltmeter with regard to, compare the ammeter and the voltmeter with regard to how it is connected in a circuit. Well, ammeter is connected in series and a voltmeter is connected in parallel. 1 mark. Then compare the ammeter and the voltmeter with regards to the resistance offered to the flow of current. Okay, so a voltmeter has a very high resistance and an ammeter has a very low resistance. Okay, low resistance, so it can pick up obviously the current, but the voltmeter has a very high resistance. Okay, done. 4.5 questions obviously intensifies a little bit. Study the diagram below to answer the following questions. Looks like they're all 1 mark. Okay, so give the readings on ammeter. Let's see. No, okay, again, no resistance here. Give the readings on ammeter 1 and voltmeter 2. So as you can see here, there's a current here of 0.5 amps and 1.5 amps. Now, what do we know? What do we know about parallel circuit when it comes to current? Current splits in a parallel circuit. So at the moment, we can see that there's a 0.5 current value going through here, so 0.5 amps and 1.5 here. So the current obviously passing and splitting here, and it splits accordingly. So that means if it's finished going through the parallel circuit, it must join up somewhere and complete back to its original whole number. So ladies and gentlemen, what is 1.5 plus 0.5? Anybody? One and a half plus 0. Oh, wait, basically 1.5 plus a half. What is the answer?
2.
2. So the reading on ammeter 1 should be 2 amps. Okay, because that's the current in the circuit. Again, current has not changed. It's the same. It's the same no matter what. Just because it splits in a parallel doesn't mean that it's changed. It hasn't gotten any more, any less. Okay, so ammeter 1, which is unknown there. Okay, easy peasy. Okay, now we could do a whole mathematical approach to give the reading on V2, but it's only for 1 mark, so it shouldn't be any different. Okay, it should be the same. So voltmeter 2 would be the same as any spot, across a parallel circuit, no matter if the current splits. So V2 should be equal to V1 here, which is 12 volts. It should be. Okay. Which ammeter is in the branch with the highest resistance? High resistance means there is a lower current, so it should be this ammeter 1 with the value of 0.5 amps. Okay. What would happen to the reading on the voltmeter if another resistor is added in parallel combination? Okay. Well, probably would be here, voltage here. Well, the answer there would be nothing. The parallel combination, voltmeter reading will not change. Okay, the resistance value will increase, but the voltmeter reading across each resistor in parallel will not change. Okay, but if resistance increases, okay, so if the resistance increases of the circuit, then and the current, whilst current stays the same, so current is still 2 amps. Okay, current is still 2 amps. Then resistance would either have to increase or decrease. Okay, but let's just do a quick check here quickly if we've got a parallel circuit. So let's say we had a resistor of 1 over 4, or let's actually work it out like this: R equals V of I, right? So that's 12 divided by 0.5. So okay, and then 12 divided by 1.5, 8. Okay, so that if we added 1 over 8. This is just random numbers I'm just working with just to see something here. Plus 1 over maybe all. Okay. Let's take this away. 1 over 6. Okay, cool. So, resistance would increase if we added in another resistor. Resistors would decrease if we added in another resistor in parallel. But the voltmeter reading across the parallel circuit, no matter what, does not change. It's the same for both. So if there was 3, it'll be the same. So that's my answer for 4.7. Voltmeter reading would not change. It's the same. And that wraps up 10 marks. Okay. Now question 5 is coming to save more or less with safety and with electricity section that we did, with we going through all the plugs and what happens and blah blah blah, and explaining the different plug points. Okay, so as you can see, typical natural science question, labeling the diagram. Okay, so I'm going to give you guys a chance to label the diagram from parts 2 to 5. Okay, they don't ask you about number 1. Okay, so maybe let's just give you guys some time to do 5.1 all the way to 5.4, because there's some more question 5 on the other circuit, on the other page. Okay, alright, so 5.1, we just have to label the plug there. So the plug there being 2 to 5. So we got number, let's see, that's the blue wire. So what would the blue wire be? Anybody know what the blue wire is called?
Neutral wire.
Fantastic, neutral wire. Alright, this was number 2, so I'll put in brackets 2 here. And then number 3, what was number 3? Was the green yellow. What's the green yellow wire?
Earth wire.
Fantastic, it's the earth wire. Okay, and then number 4, let's have a look here. What's the brown? Okay, what's the brown wire?
Live wire.
It's the live wire. Let's take this away there. The live wire. Alright, and number 5, who knows what number 5 was?
A fuse, I think.
I like the way you think. It is a fuse. Okay, that's pretty basic, pretty simple. 5, I think that should be what? 5? 4 marks? 4 marks. Excellent. Good stuff. We can explain the purpose of part 3. Now, part 3 was the earth wire. So I'll kind of bring 5.2 into this part as well. Let me just give an explanation here. Someone please explain the earth leakage. What is it for? What does it do?
I wrote it stops the appliance becoming charged with electricity.
Fantastic. Okay, I'll take that as an answer. Let's get there. Okay, I'll take that as an answer. Stops appliance with or becoming charged with electricity. Charged. Electricity. Okay, great stuff. Okay, so it's basically the safety device that's used in appliances. Well, not all appliances. Like I know TV screens or television sets, they don't come with an earth leakage, but especially appliances, some appliances and power tools, they have earth leakage. It's to prevent the person from getting charged with a shock. Alright, so basically it detects stray voltages on metal enclosures of the electrical component and interrupts the circuit of if a dangerous voltage is detected. So in other words, it basically looks after people so that we don't become shocked. So if the earth leakage is damaged or the earth leakage wire is not working properly, then of course that accidents can happen. So it's very important that we check that the earth wire is doing good, because obviously it provides us with some safety when using power tools. Excellent. 5.3, identify the wire with the lowest resistance. Write down only the number. Okay, so 5.3, let's go back to the diagram. Which wire has the lowest resistance? Which wire has the lowest resistance? Just the number.
Number 3.
Number 3, which is, of course, the earth leakage. It has the lowest resistance. In fact, it is almost zero. Okay? The reason why it has to be almost zero, so if a stray electron, all right, it can be easily absorbed. All right? It can be easily detected and discharged. Okay. 5.4. Okay, I haven't read this question yet, so let's see if it's viable to do in this time, since we only have a few minutes left of the session. Before World War II, some radios got power through a resistance cord that had a significant resistance. Such a resistance cord reduces the voltage to a desired level for the radio's tubes and the like, and it saves the expense of a transformer. Explain why resistance cords become warm and waste energy when the radio is on. So this is basically a reasoning and motivation question, obviously using some form of facts, of course. Well, we know that when something affects, or what affects, resistance. Okay, and of course we know what affects resistance. There are 4 factors. Okay, so the question is, explain why resistance cords become warm and waste energy. Okay, well, if a cord becomes hot, that means the temperature is increased. What does that mean? An increase in temperature of the wire increases the resistance. Also, looking at the explanation, they had a resistance cord. It had a significant resistance already. So now when it gets warmer, the resistance already increases. All right? So now wasting energy means now more energy needs to be supplied, which is voltage, in order to get the current to flow. Okay? So they said there that such a resistance cord reduces the voltage to a desired level for the radio's tubes and the like, and it saves the expense of a transformer. But now the resistance is now increased. So if resistance is now increased, that means the flow of electrons obviously will not be as easy, or won't be as easy to pass through, because your electricity is now increased. Also, if you reduce the voltage, okay, that means your electrical energy is now lower. Okay, and according to Ohm's law, if your resistance is high, your voltage is lowered, and your current is also lowered, then you're going to have an increased resistance, and then that therefore wastes energy because your resistance is so high. So that's just using the factors and Ohm's law in tune. Does that make sense to everybody?